Welcome. In this video we are going to show how to use the DiMAT toolkit materials processing simulator designed to simulate material transformation process. First, we introduce our credentials on the login DiMAT toolkit. In this case, we will access to the materials processing simulation for manufacturing polymeric materials to replicate an extrusion process. For create a new simulation, we select Run New Prediction, then we choose the name, this one, and in this case, for our example, we will introduce a diameter of 0.004 meters, a temperature of 180, and a screen speed of 250 rpm, an extrusion coefficient of 0.0005, mass in extruder of 0.25 kilos, and finally shear rate of 200. Then we select our material, in this case polymer 01, and we press run. We can see on the screen a successful simulation did was appear. Then we select to see our predictions, we check the parameters of our simulation, and we select view of output. On the results section, we obtain different kinds of information. First, percentage of survival and degraded material fraction. Secondly, a twin screw extruder visualization. The 3D viewer use your simulation input temperature to compute a realistic thermal profile along the extruder zones. Pellets are colored according to this scale. Then we can observe the 3D model, and we can do a zoom for be accurate in our analysis. If we need it, we can select the button Info to check our zones. From the results obtained, we can plot a graph residence time versus degradation. In this scatter plot shows how the residence time inside the extruder influences material degradation. Each red point corresponds to a past simulation. The blue point corresponds to the current simulation. Higher simulation is often associated with longer residence times, since the material remains exposed to mechanical stress and heat for longer. This chart helps identify process conditions that could minimize degradation. We also can plot on our graph volumetric flux versus residence time. This chart compares the volumetric flux with the residence time to evaluate the balance between productivity and material quality. High volumetric flux implies higher productivity, but it can also reduce residence time, affecting thermal homogeneity or mixing quality. This chart helps determine optimal conditions where productivity and thermal control are balanced. Finally, we select material condition. In this pie chart, visualize summarize the fraction of material that survives without degradation and the fraction that undergoes thermal or mechanical degradation. Green for material in good conditions and orange degraded materials. In our case, 97% of good quality material versus 2.57 degraded. After finalize our results analysis, we can go back to the initial screen with Dash Brush, MPH Polymer, and then we can develop our results of all our simulations, and a message of successful simulation developed will be appear on the screen. We invite you to explore the full potential of DiMAT platform. And if you are interested or you have any questions, don't hesitate to reach out using the contact information below. Thank you for watching.